let's go ahead and get started. So Solana 101, right? To kick things off, this is going to be a little bit of our agenda here that we're going through. And don't worry, we'll go through this bit by bit. But to start, we're going to talk a little bit about some of the technical advantages of Solana. So obviously, if you guys are here, you probably know a little bit about why you might want to build on Solana. But in a nutshell, the biggest reasons are going to be one, very, very fast confirmation time, right? So super fast time to confirm blocks, which means when you're building an application, your users don't have to worry about like waiting a long period of time to be sure that something was done successfully or to find out if there was an error, what have you. So that's super important. And also very low transaction fees, which, Solana is very famous for. So when you're building stuff, it helps to have really low fees because you can actually introduce more like robust functionality and you don't have to worry as much about what it's going to cost your end user. So with that being said, Solana maintains both these things all while maintaining a 2,500 plus validator network. So pretty impressive, pretty decentralized, and growing fast. So anyway, let's talk about a little bit how the network actually works, right? So how it creates new blocks, how it kind of processes transactions. What are some of like the key innovations and components there? So to start, just like most proof of stake networks, Solana actually uses an elected leader per block creation cycle, right? So every time a new block needs to be created, one of the validators of the network is elected as a leader. And what that basically means is that node is responsible for creating a new block. And the cool thing is, on Ethereum, you have something like a mempool, right? Which you might be familiar with. And that's just a big giant queue of transactions waiting to be packed into a block. And the way those nodes sort of do that is, they go and grab them out of the queue. And that queue is kind of like a shared memory. On Solana, it actually works a little bit differently. So Solana will actually forward transactions to the leader ahead of time because it knows it's going to be the leader next. And that way, once that leader is elected, it has all the transactions sitting there already. So it can just immediately pack the block and put all those transactions in there. And, that obviously optimizes a little bit for speed. And then once that process kicks off, that leader can also disseminate information from that block out to the rest of the network and let everybody else know what it just made, right? And so what this actual engine is called is technically Turbine, and it's a really high throughput way of actually disseminating that info. And thirdly, when the block is actually executed and all those transactions are run and all the instructions inside of them, which we're going to talk about, are kicked off, they can actually run in parallel because Solana actually operates a little bit like a thread pool manager. So if any of you guys have worked with like multi-parallel processing, multi-threaded processing, or anything like that with your programming, you know kind of what I'm talking about, right? So if something needs to be used, it needs to be written to, then a lock will be placed on it. If it's just going to be read, then that can be optimized parallel. That's exactly how Solana operations kind of work, and we'll see that close up as well today. So those three things are really helpful for making Solana as fast as it is, right? Super high throughput, high transactions per second. And one of like the more popular innovations behind Solana as well is the concept of proof of history. So what proof of history kind of is it's a way for the nodes to reach consensus on the passage of time. And like without getting too technical how it works, imagine you have like a hash function. In fact, that's pretty much what it is. You have a hash function that with somewhat like very, very precise certainty that that function is going to take X amount of time to run every time you run it, right? So no matter how many times you run it, it always is going to take the same amount of time each time. And so what, proof of history basically does is it starts with one hash and it puts it into the function to create a new hash. And then it takes that created hash and puts it back in and it will create a new one every time, right? And so if you count how many hashes there are, you can do the math of how much time has passed. And what's cool about that as well is if you have all the hashes, you can slice that list of hashes up and you can go through and run that calculation yourself and you can validate that it's actually legitimate, right? And the benefit from slicing it up is, you wouldn't have to go through all of that time just to validate it. So, pretty cool overall, a way to reach consensus on the passage of time, which is up to recent times, up to present, a very, very difficult thing for decentralized networks. So, decentralized clock, so to speak. So, pretty cool stuff. So, a couple of takeaways from the network overview. Solana has really fast confirmation times, low transaction fees, no mempool. It can execute programs in parallel, and it's ideal for high performance applications. So, does anybody have any questions about like the network overview aspect of things? Does all that kind of make sense? All right, cool. If anybody does have any questions, feel free to go ahead and pop in. So, cool. So, that takes us through the network overview. Now, we're going to talk a little bit about the actual programming model. So, building on Solana, what are the things you need to know? Like, how does it kind of work? What are the concepts that you need to understand? And to start, we want to cover the concept of accounts, right? So on Solana, everything is an account. And I pretty much mean everything, right? So anything that has any kind of data is an account. And that's basically just a little like slice of data from the blockchain. And it's indexed according to this account model that we're going to flesh out here. So some rules about accounts. Each account has a unique address. Each account holds some balance of SOL. And accounts can store arbitrary data. And based on how much data you actually store in that account, you have to pay what's called rent. Now, rent, as like a quick overview, it just means that like you want to occupy some space on validator hardware for whatever you're storing. And so the concept of rent is there to, kind of incentivize people to basically be very not conservative, but aware of what they're storing and try to optimize these storage solutions where possible. So you put a little, real, almost negligible amount of SOL, depending on the size of the data, into the account, and that takes care of your rent. And technically speaking, you just have to put in enough rent to be considered rent exempt, which is something you can learn more about as you build a little bit more on Solana. But what that basically means is if you have enough SOL in there, they won't take any out. So kind of cool. Um, Moving on, a couple more rules. Anybody can credit SOL to an account, and anybody can read from an account because it's a blockchain, right? So it's public information, public ledger. So that makes sense. And then conversely, only the account's owner is authorized to debit SOL from the account or modify the data within it, right? So that's a really important concept that we're going to kind of loop back to periodically throughout this talk. But again, only the owner can do modifications to the account. So here we're going to take a look at what an account looks like up close. So this first field here you can see is the key. That's just going to be the address of the account. And then Lamports, that's going to be how much, SOL is in that account. Lamports being that smaller denomination of SOL. Data is going to be the, buffer that stores just whatever kind of like arbitrary data you've put in there. And then is executable? Is this account, is the data inside this account a program, right? Is it executable as a program? And finally, that owner field that we talked about. So this owner field, this address is always going to be a program. And this is the program that has the right access to this account. There's only one at a time. So speaking of programs, we'll talk a little bit about those. Programs are basically akin to what you might have called smart contracts in other languages, but there's plenty of nuanced differences between what people know as smart contracts and Solana programs, and we'll see some of those in play. But basically, they're very similar. You can think of them as similar things. So, like we talked about, everything is an account, and this includes programs. We saw what that is executable field, and special kind of account that has an executable program within it. And right now you can write programs in Rust, C, C++, or Python, but hopefully soon you'll be able to write programs in other languages too, like TypeScript and Golang and, who knows, maybe even more. So that'll be interesting to see. And then some rules about programs. They are actually stateless. So this is what I was kind of talking about when I was mentioning the parallel execution and I was talking about everything being an account, right? Programs don't house their own data internally like they might on like Ethereum with a smart contract. Instead, they just operate on other accounts that live on the chain, right? And if they're the owner, they can modify the data. And because it's operating on data that's sort of external, so to speak, from the program, that's what allows that whole like parallelization of it. So pretty cool stuff. Conceptually, programs they process what are called instructions, and we'll see those later. Um, and programs can also send those instructions to other programs as well, right? So like think about like you might need to do something to an account that your program doesn't own, but then you might need to do something else right after or what have you. You can actually go invoke another program and come back to yours. So, very interesting. So, takeaways from that section, everything is an account. All accounts hold SOL. They can store arbitrary data. They can also store programs, and accounts are passed into programs to perform actions on data, which allows for the parallel execution that we talked about. So, anybody have any questions about those concepts at all?
If anyone has questions, we do have some mics, so just feel free to raise your hand and we'll run one over. Doesn't look like it, Joe.
Okay, cool. All right. So, moving right along then, I mentioned we're going to get into instructions and transactions. So, that's what we're going to talk about right now. So, we'll talk about instructions, which are, the mechanisms for actually invoking a program. So, an instruction looks like this in its raw form. There's going to be a program ID.
Joe, stop you really quick. We actually don't see what you're sharing. We can, if we're just looking at something.
What happened?
There we go. Perfect. We can see it.
Oh, cool. Were you not able to see it until now?
Joe, are you still with us?
Yeah, I am. Sorry.
Okay.
Okay, cool. Anyway, so now that you can see that, what I was basically saying here is I'll walk back just a step or two. So the program ID from the instruction, that's going to be the program that this instruction is actually for. So like if this instruction was like telling your program to do something, this is going to be your program's address. And then the accounts involved in the instruction, this is just a list. And you can see that the key, the address of the account, and then these two fields here are actually crucial. So the mutable field and is signer field. The mutable one is actually what kind of tells the Solana runtime whether or not this is going to be, you know, something that needs to be locked for a write or if it can just be read in parallel. So that one's super important. And then is signer, right? Is this account one of the signers on the instruction or on the transaction? And that's going to be a check there to make sure that like if it's going to be mutable and if it needs to be a signer, that should be true. And then finally, you got your data, which is basically going to just be whatever action that you're doing plus any kind of like parameters or arguments. So speaking of transactions, these are actually the vehicles that you use to send instructions to the Solana network. So here's a little quick overview of how these work, and we'll break this down some more. But basically, a transaction gets sent to what's called an RPC client, and that client is able to communicate with the validator network directly. And that is how you get your transaction into the network. You go through one of these clients, it forwards your transaction in, and then it can be processed like the diagram we saw earlier. So anyway, transactions look like this. So breaking these down kind of like we did the instructions. The first thing you notice is we have a list of instructions. So you can actually put more than one instruction into a transaction. So like if you wanted to do maybe like 6 different things in order, you can just put them all in this list and send one transaction. So a little less gas fee, a little bit faster. And the cool thing about that is these transactions are also atomic. So what that basically means is like if you include a handful of instructions and any one of them fails, whether it's the first one, last one, doesn't matter, the whole transaction is going to fail, right? So this is a security measure, and it actually comes in really handy for things like a sale of an asset, right? So if you wanted to like sell an NFT, you would collect the payment, and then you would, issue your NFT out to the person, or maybe you wrote the instruction where like you give the NFT and then you get your payment. If any one of those failed, then the other party would clearly miss out, right? So that's why that works like that. And then just real quickly, the recent block hash is there to kind of weed out duplicates. And then the fee payer is who pays for the transaction fee. So there's always going to be one fee payer, and that person has to sign the transaction. So we kind of touched on this earlier when we saw the is signer field from the instruction. And basically, what's happening here, especially when you want to be the one who pays for the transaction fee, like you have to sign, that list of signers at the bottom, that's just an array of buffers, and each buffer is going to be the whole transaction encrypted by the signer's private key. And so, for those of you guys who don't necessarily know maybe how it works, in cryptography, if you've got a key pair and you sign or encrypt something with your private key, and if I can decrypt it with your public key, then I know and I have like verifiable proof that you do have the private key, but I don't need to have your private key, right? So that's like the fundamental concept. So when it comes to a transaction, you can encrypt it, we can decrypt it on the Solana runtime or on chain, what have you, and thus make sure that you did in fact sign it. And this serves as an authorization for different kinds of actions, such as like debiting Sol to pay for a transaction or like changing data. So that's going to be what that what that field does right there. So anyway, some takeaways there. Programs are invoked by instructions. Instructions are sent via transactions. Those transactions are atomic, and transactions must be signed. So does anybody have any questions about instructions or transactions? All right, cool, 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 cool. So moving along, this is where things might get a little bit more complicated, but this is where some of like Solana's design, decisions really come into play and actually serve some powerful use cases here. So the next stage that we're going to talk about here is working with custom data for a program, right? So far we talked about accounts, programs, transactions, and we talked about how these accounts are separate from the program, and the program has to use them to basically manipulate data external to itself. So, like, how do you actually do that? And how do you create data that's going to be specific to your program and that might be custom to whatever your app is doing, right? So, let's revisit that whole concept, the concept of account ownership, stuff like that in a different light. So, if we think about like a traditional Web 2 app, these apps can read and write from their own like database pretty much at will, and that's kind of like the de facto setup. So, how do we replicate this kind of behavior on Solana with, a smart contract or a program and with data that it can actually do the same kind of thing to? Well, for starters, we obviously are going to need to have a program that is using a collection of accounts that it in fact owns. So that's going to be stage one. We have to make sure that those accounts are all owned by the program. But then we get into the concept of like, what if we need to create many accounts? We need to have some kind of ordering going on or some kind of like indexing or relations. So similar to how databases work, at least SQL. So that's where the concept of a program derived address actually comes into play. And this is going to be one of the concepts that trips a lot of people up when they're onboarding to Solana. So I'm going to try to explain it in the context of a database here. So, first of all, with a program derived address, you can derive the address, as the title suggests, from a function. And that function is called something different. I'm just calling it a hash function here for simplicity. But the two parameters you're going to use are a list of seeds and then a program address. And that program address is typically the owner of that account, but it does not have to be. And then those seeds can be anything, right? Like they can be other addresses, they can be strings. They just have to eventually serialize into a buffer. And then you can just have an array of buffers as your seeds. This will make more sense in a second. So, anyway, another feature of these types of accounts, any account that's a program derived address, if we take a look at the traditional way of changing an account's data, right? Right here, we have a traditional system account, key pair, standard. Basically, you can think of it like a wallet. That account is going to sign a transaction, which is going to authorize a program to change its data, right? And it can update the state because the signature's been provided. However, with a PDA, you can actually send a transaction that this PDA did not sign, right? And I say unsigned transaction, that just means this thing didn't sign it. Someone has to sign it for the fee. But you can see here that we have one more additional step involved here now that occurs on our program's actual like operation. And that's where the program is actually using those seeds to create a signature or basically to authorize a change to this account. So the cool thing is there is no private key for these accounts. The program can actually authorize changes to this account without any kind of private key signing for it. And those seeds are involved in that process as well. But the point is, you can basically have data that the program owns and can sign for, and then it can change completely at will whenever it kind of wants. So, pretty powerful stuff. Now, let's take a look at this in the database perspective here. So, we got this table, and this is just going to be some profile information for people, right? So, the table name, profile, and we got 5 records. And you can see we're just keeping, some bits of information about somebody's profile. But the important piece here is, like a database, you might have like a primary key field, but consider this address field as like a foreign key, right? And we are actually going to house everybody's wallet address. So for my wallet address, I'm Joe C, and there's my email. And so obviously we know that like, hey, if I have your wallet address, I can just look through this table and I can find the rest of your profile data. But how could we do this with like a PDA and like some seeds that we could use to derive this address itself? So consider each of these records as an account per se, right? And if we consider the table as the account's like structure, then we can do something like this. We can basically make our seeds be the profile word, like the constant. And then we can also hash that with the wallet address and of course our program's ID. And then in that account, we can just store the data that we're talking about here. So you can already see how you previously would do this with a database table and records. You can kind of transition directly over to, a collection of PDAs. And in this case, every time I provide a different wallet address, I'm going to get a different, you know, piece of profile information, different record. And if this account doesn't exist, of course, we know there's no record for it. And then taking a look at another example too, if we have a table of like posts where we're just keeping track of like, I don't know, like how many times you've posted on like a website or something, then you can see here we're linking to your wallet address, but also your address of your profile record. And this is just an example. So how could I like set up this relationship as well? Well, similar fashion, I can just use a constant and then I can use the wallet address and the profile address. Now, this particular derivation might not be completely necessary, but it's an example to show you of how you can add parameters into these seeds that will change. And based on what those are, you can basically find different data and you can relate across these accounts as well. And we'll see later on actually that this technology powers how the SPL token standard actually works. So, a couple takeaways from PDAs. Account addresses can be derived from seeds. PDAs can be used to relate data across accounts. And PDAs don't have private keys. The program can actually sign for them. So that one's usually a little bit tricky for people. If anybody has any questions, grab a mic. But I'm gonna probably keep moving along anyway, just because I don't want to just keep stopping. But if anybody has questions, feel free to stop me. So let's tie everything together that we just learned in all of those like programming model concepts into sort of like a walkthrough that'll kind of like link everything together. So tying it all together, let's take a look at this example here. We're going to just use one account. It's going to keep account, and that's just going to be an integer. And we're going to have one instruction on our program, which is just going to be responsible for incrementing that account. So every time we call the increment instruction, it's going to just increment that count by one. So to kick things off, we're going to start with a decentralized application or a DApp. And this is going to be our client, right? And so from here, our user is going to like click a button or do something or perform some kind of action where basically they're going to interact with our app and it's going to send a transaction to our RPC client, which is exactly what we talked about earlier. And so we send that transaction over, and then the RPC client is going to forward that transaction to a validator, right? And then once the validator has the transaction and it processes it, similar to the diagram that we kind of opened up with, then it's going to invoke our program because let's, assume in that transaction is an instruction for our program. So it invokes our program. And when our program is invoked, it actually runs that increment function and it will modify the state of this counter account, which it owns, to be now one, right? And that's how these pieces kind of all fit together. So, just to quickly recap, the client kicks off a transaction to the RPC, that forwards it to the network, that transaction is processed, the instruction runs our program, and our program owns that account, so it's able to go change its data as a result of what the instruction told it to do. So cool. Takeaways there, applications send transactions to RPC, RPC forwards it to the network, validators execute the transaction, and then a program can update account state. And in that order is how this kind of happens. So that ties everything together for like the programming model and the programming paradigm for Solana. So if you guys could understand all that stuff and you feel like you got all that confidently, then you should be in good shape to start, looking into building on Solana and maybe getting your feet wet with some tutorials and stuff like that. But I'm going to talk a little bit more now about what's kind of like hot and pressing on Solana, and that is going to be tokens, right? So what most people are interested in some fashion or capacity, are tokens. And this could be tokens in like their natural form, or it could be NFTs, right? And we'll talk about both. So getting started, there's a number of programs on Solana that you can use to create tokens. So compare that to something like Ethereum, where to create a new token, you need to actually deploy a smart contract. And that smart contract builds your token and kind of sets up all the different features of that token. Instead, on Solana, what you can do is you can use existing programs to create a token. So you don't have to deploy any kind of program, and that actually means you don't have to write any Rust or anything like that. You can do all of this stuff from the client side. You can just send transactions to the network and you can create tokens. And then you can do stuff with them, you can mint them, you can transfer them, stuff like that. So really important to understand. But with these tokens that exist already, we can actually create tokens and they follow the SPL token standard. And this is a little bit of an overview of how that standard looks and how the state kind of works for these different components. So, first things first, we have a Mint account, and that account is literally your token. Like, that is the description of the token. It has some details about it, and there's only one Mint account for any token. So, you might be wondering, like, how do you send tokens to people or like mint new tokens or things like that? Well, you actually have to make use of a related account called an associated token account. And if you look here, you can see that like I've got this wallet. And if I want to know the balance for my wallet of a particular mint, then I basically have to bridge between the wallet and the mint by creating an account that's related to both that can store the balance of the mint for that wallet, you know? So that's what these accounts basically do. And we'll look at these a little bit closer in a minute. And then also if I wanted to add any like photos, like if I wanted to add like a JPEG as they call it, or different like strings and associated like metadata or information to a token, that doesn't actually go in the mint. The mint is a very specific, set of data. It follows a standard. If you want to attach additional metadata like symbols and icons and stuff, you actually can create related accounts called metadata accounts. And this diagram right here shows you how these pieces kind of fit together. So the mint is related to the metadata account. And again, like I said, the associated token account ties together the mint and the wallet. And these dashed lines that you're looking at, these relations, these are the PDA seed patterns that we kind of covered already. It's using the same exact technology. And so we're going to take a look at what these seeds kind of look like, and we're going to see that up close. But first, I want to just cover this is just to really drive the point home that like you can do all of the creation of a token completely from the client side by just going to the RPC. So if you just put these four instructions in, you can mint somebody a new token, right? So create an account, make sure that account is initialized as a mint. Those are two separate instructions. Create an associated token account and then mint new tokens to that associated token account. If you put those four instructions in order into a transaction and send it, you get an SPL token. No contract, no program to deploy. You can write it all in JavaScript. You can do it from Postman. You can do it in a number of different ways. So anyway, takeaways, again, you don't have to deploy a program. You can create new tokens with RPC calls, and related accounts are used to describe tokens. So moving on to some of the more like, I guess we'll do kind of like a diagram here, like an overview of minting an SPL token. And this will kind of be similar to the diagrams we walked through earlier, but it'll help you kind of like visualize and contextualize how this thing kind of works. So to start, I'm going to do this in like sort of a generic fashion. I'm going to show you another iteration of what we just saw with the like list of instructions. So we start out by creating a new account for the mint. And to start, we basically determine how big this account needs to be because we know it's going to be a mint, but we don't write any data to it yet. Instead, we just create it. And then the second thing we do, as we saw in that first diagram, is we initialize that account as a mint. And this is where we actually write the data into the account so that we know it's a mint. And we'll see that data in a little bit as well. And then we optionally can create any desired metadata accounts, which I did not include in that transaction earlier because it is optional. But if you wanted to have, like I said, like an icon or stuff like that, this is where you would kind of do it. And then once we do these three things, we've technically created a token. It's done. The token exists, the mint exists, and it's valid mint, but the total supply is zero, right? So in order to introduce new supply of a mint, what we have to do is mint new tokens to somebody. So we take somebody's wallet, for example, maybe it's your wallet, maybe it's a friend's, what have you, and you set up an associated token account. And once that account is set up, then you can go ahead and mint new tokens to it. And that will just increase that balance of that associated token account, right? Like we talked about earlier. And that is the process right there of introducing new tokens. Now, it might be obvious to you guys, but if you've already done the top three blocks, like you only have to do those once, and then you can just continue to mint new tokens all you want, as long as you don't have a fixed supply of some sort, and as long as you aren't working with an NFT. So anyway, let's take a look at this in a little bit of a different light. Let's create a custom Joe token here, just to really drive the point home, and because I wanted this photo on there of me because it's hilarious. So to start, again, creating a new account for this mint, no problem. Initializing that account as a mint, okay, same as we just saw. So now we've got this thing set up. It's a valid mint. And now, how do we get my photo on that token, right? How do we get it to come up in Explorers? How do we get it to show up on websites and wallets, things like that? We go ahead and create a metadata account. And once we do that, we are good to go. Our token's set up. And then if I want to just like mint a couple friends some of my tokens, which by the way, you can do without their permission, which is hilarious. You can just create associated token accounts for their wallets and just airdrop or mint to their associated token accounts, and they don't have to sign anything for that. So you can make a token of your face and airdrop it to your friends as long as you have their wallet address. So make sure you go get those if you don't have them. It's hilarious. So anyway, we create those associated token accounts, get those set up. And once those are set up, we could do exactly that. And we can just go airdrop those tokens. And then your friends wake up and they've got your face on a token of some quantity in their wallet. And that's it. So that's how you basically go about doing tokens on Solana. Um, so this is the token standard, right? This is all the different components of the SPL token standard, of the metadata standard. We covered both, and they're very intertwined. But what we didn't really cover specifically here is NFTs. So just to mention, like NFTs are part of the SPL token standard. They are SPL tokens, but they have like other details about them that make them unique to NFTs. So talking about NFTs, those unique properties of NFTs that make them what they are, they're going to be 0 decimal places, and they have a total supply of 1, right? That's basically it. And 0 decimal places just means, in a general sense, you can't break up an NFT into smaller, denominations of itself. So like a dollar, you can do cents. An NFT, you can't do that. There are things out there like fractional NFTs and stuff like that, but it's not exactly, um, it works a little bit differently than what this is describing. For the most part, NFTs have a supply of 1, 0 decimal places. That's it. And the cool thing too about NFTs, as you can see from the snippet here from Magic Eden, is they actually have super highly customizable metadata. And so, NFTs on Solana are huge. They're super, super popular, and that's because of all the cool stuff you can do with them. So, like, a couple examples might be like a master edition, and like you could do like printable versions of a master edition. You can make an NFT belong to a collection, right? You can have royalties for the creators of the NFT. And then you can even expand on those existing pieces that you can create, and you can create your own, right? You can write your own program, introduce your own accounts that, add supplemental data to NFTs. There's the introduction recently of programmable NFTs, all this kind of stuff. So, tons of stuff to explore with NFTs. The ecosystem is growing really fast around those. So, anyway, the basic takeaways for NFTs: 0 decimal places, supply of 1, highly customizable metadata. And so that basically covers everything for those 3 blocks, right? So we went over the network, we went over the programming model, and we also went over tokens and NFTs. And so the last thing that I want to cover here is I'll go into a little bit more detail of what these accounts look like as part of the SPL token standard. And just in case anybody wanted to know what these looked like up close, or if you're curious. So we're going to see what these accounts look like. So starting with the mint, this is the data that's contained inside of a mint. So is initialized, obviously, whether or not it's been initialized as a mint, the total supply, the decimals, right? And then, again, like we said, NFTs, zero decimal places. And then the mint authority. So that's going to be the account that can actually mint new tokens. So if you want to run that like mint to function that we saw earlier, you have to be the mint authority. So when you create this mint, you set this value, and then whoever this is set to has to sign to authorize the minting of new tokens. Similarly, the freeze authority kind of operates the same way, except when you freeze a token, you freeze it in somebody's associated token account. So, no credits or debits of that token, of that associated token account until you thaw it. So, even more hilariously, you could airdrop a token of your face to your friend and then freeze it, which is hilarious. Anywho, moving on to associated token accounts. Here I'm breaking down the seed pattern and also the data, right? So just keeping it balanced, nothing special. But here's how those seeds are related to one another when it comes to bridging the wallet and the mint together. You can see that they're just part of the seeds list and they're just hashed with that associated token program. So following that pattern, that standard, you're always going to be able to find an associated token account if it exists. And then metadata accounts, same kind of thing, right? We've got a pattern to derive metadata accounts that looks pretty similar, except we're making use of a constant string instead. And then the data in a metadata account is honestly much bigger than what I'm showing here. And there's other types of metadata accounts, which we touched on, that you can really expand this out. But I've included some of like the more popular and common ones. So like royalties, I don't have in here, but those are definitely going to be part of it. And then you can see the collection that this NFT might belong to, or this token. The blue fields are more specific to NFTs, just as a caveat here. So you've got like the creators; those would be the ones who would collect the royalties, the collection that this NFT might be part of. But then the other fields actually can go for either just SPL tokens or NFTs. And the first one being the update authority, that's going to be the account that's allowed to actually change this metadata. So you can make metadata mutable if you want, and you can just give somebody the authority to be able to change it. So like what's cool is like some people will do that with NFTs where they'll basically make like the metadata change over time, or like you'll have like a, I don't know, like a little geopet or something where it like grows over time. That's kind of how they do that thing. So with that being said, the data inside the data field of a metadata account, a lot of datas, that's going to be your like most commonly used like set of data for token metadata. Title, symbol, those are the things that you see pop up on exchanges, explorers, all those things in your wallet. And then the URI is actually a URL that points to where the image is actually hosted. So for those of you guys who might not know, it's very rare that an image itself or any kind of like similar asset would be stored on chain. It's not really super practical. Instead, there are decentralized networks that are basically solely designed to store things like images. And what you can do is you can host your image there. And there's all sorts of security layers as well. They're pretty decentralized stuff. And then you just point to that location using a URI, and you store that pointer inside of your Solana metadata account. And that's basically how you set up like a photo for an NFT. So anyway, guys, quick takeaways from those like state overviews. Mint accounts house data about the mint. Associated token accounts store the user's balance of the mint, and then metadata accounts have the metadata for the mint, which can be completely expanded, depending on what you want to do. So that's really it. That's all the basics for Solana, guys. And I would love to take any questions you might have right now. But hopefully you guys learned something. Hopefully that was helpful. And yeah, I think you guys are good to go, ready to build.